Yeah, let's get started. Hey, folks, thank you so much. I know it's almost the end of the day. Really appreciate you coming into our session. Good afternoon. My name is Fahad Khan. I'm the head of product, and today I'm here with Naveed Farooqi. She's our head of data and CVML platform, and together we will be sharing with you the journey that we have been on in enabling multiple autonomy and automation initiatives at John Deere. Before we get into the heart of the conversation over here, we do want to set some context. BlueRiver is a subsidiary of John Deere, and us as a company, we focus on three main things: robotics, computer vision, and machine learning. Our mission is actually quite simple. It is to create intelligent technology that makes a tangible impact in accelerating various sustainability initiatives across the agricultural space. BlueRiver's first smart machine was actually a lettuce bot, which was then very quickly replaced by the iteration in precision agriculture, very fittingly named See and Spray. Why See and Spray? Because if you see a weed, you spray it. Technically, it was not so simple. We, See and Spray actually utilized deep learning to actually enable our machines to identify a wide variety of plants, including many different types of crops and weeds. Not only just identify them, but identify them with accuracy and make crop management decisions on the fly. What we were really excited about over here is with the success of See and Spray, many different programs actually started, many different initiatives started to spawn. And when they started to spawn, we knew that a platform is actually needed. A platform where we can create an ecosystem that could sustain and grow an entire life cycle of computer vision-based machine learning. So then we started to think about what should be the guiding principles of creating such a platform. So we knew it had to be scalable, performant, and cost efficient. In addition to this, we took a look at our challenges. Our biggest challenge was not just only dealing with petabytes of data and acting on it really quickly. It was probably much more higher because we had to scale the same technology on hundreds and thousands of tractors and other John Deere machines. So, without any further ado, Naveed, do you want to tell us a little bit about this data and CVML platform that has been doing all these great things?
Yeah, sure, Fahad. Next slide.
Just click.
Didn't blanked out. All right.
There you go.
So a little bit, it's just an introduction to our Accelerator platform. It's a CVML Accelerator platform for John Deere's A&A Leap ambitions. And the way it is built is it's an integrated ecosystem of infrastructure, data, tools, application, and a lot of vendor workflows. And we'll explain why we've done integration with vendors really to enable agility in this very fast-moving space. And it's an entire ecosystem that just enables these engineers. We basically are an internal engineering platform. So our consumers, our end users, are data scientists, machine learning, and software developers. Fahad will talk a little bit more about their needs. But it is essentially enabling these engineers to actually have the complexity of infrastructure removed from them so that they can actually focus on solving domain problems. So over to you, Fahad.
Yeah. So if we will get into the details of it. You will see a pretty detailed design that Naveed will walk you through. But we do want to set some context on, what's our vision? We want to be the go-to platform for any data and CVML needs in our organization. And we are really driven by our mission, which is empowering not only existing programs, but new autonomy and automation programs, both at BlueRiver and John Deere, to make sure they have a sustainable ecosystem of model management, end-to-end model management, and machine lots. Our success is not only measured by how quickly we can bring new programs to life, but also how efficiently we can scale existing programs. If you take a look at who are our current customers today, they are some of the more established programs that you might know about. You may have read about them in the news. See and Spray is one of them. Autonomy on tractors is the other one. Smart Detect is also a pretty established program. And then this platform is also being used to scale newer programs like construction and forestry. If you take a look at within these programs, who are our actual users, right? These folks are your ML engineers, software engineers, data engineers, product managers. All of these folks are highly technical, and they value innovation quite a bit. Their goals are to solve very hard problems while not letting cost get out of hand. So that is one of the driving principles that we actually have. So that is why when we were designing this platform, we wanted to ensure that when we serve their needs, we create something that does not take away the independence that is needed to innovate, while at the same time balancing and providing them with the wins that are needed to scale, and ensuring anything that is within our platform, whether it's products, workflows, those are set up for success and scale and being cost efficient. If you take a look at what are some of the problems these folks actually face in their day-to-day lives, right? Most of them are self-explanatory. I won't go through all of them, but one thing that I would say that it is, if you work in this space, you would realize that it is no secret that the success or failure of any machine learning team or program, it really depends on your data management strategy. Over here, their biggest, not only we have to ingest petabytes of data, we have to be able to explore it. And it's one thing to say, explore it, you have to find the relevant data. Why do you want to find the relevant data? Because you want to be able to identify challenge conditions that might already have been discovered, or maybe you're looking for something new. So you can create the relevant data sets and eventually train your models. But above all of this, the biggest thing to highlight over here is, and I'm sure you make these requests from your platform teams too, creating an abstraction around infrastructure, creating an abstraction as much as possible around data engineering and ML ops, because what we want to enable these users to do is do their job, which is churn out models as quickly as possible without worrying about data engineering, ML ops, or infrastructure as much as possible. So at a high level, and we will dive deep into the technical details of how we are solving these problems for our customers, but at a super high level, if you were asked me, how do we solve this for our customers in a single line, in a single sentence, I would say by providing them with a unified machine learning and data platform. I understand that, on this slide you may see log analytics is number 5, but when a machine is actually in production, what we really need to understand are the messages that are coming off that machine, being able to replay that situation, to really understand what actually happened, when did the machine behave, like how it was supposed to behave, and when it did not behave, when the expected behavior was not there. So then we try and replicate that situation. We try and simulate that situation to find the right images. Once we find the right images, then we try and label them if it's a new use case. Labeling, for the most part, could be automated, but there's some human labeling involved as well. And eventually, those images grows into improving the model. And then there's continuous monitoring on model iteration. So we can see how is it performing, is it doing what it's supposed to do? And eventually, the models get released. So without further ado, Navi, do you want to?
I think the slides are, okay, that's good. Yes,
okay.
That's okay, yeah, okay. All right, so talking about the new platform stack. This slide is a little bit personal to us people at BRT who are here, and maybe the folks at Databricks. So it's a bit of a personal slide because it's actually the journey of our story, of the journey of our platform in the last 1 year, or really probably 8 months. I think about a year ago, we were a simple CVML offering with a data lake sitting on AWS S3. We had curated data stores, Mongo, Elasticsearch to do some purposeful data storage. And we had our entire ML ecosystem running on open source Kubeflow. And while this was definitely very helpful, it laid the foundation for the programs to start, as we started to scale, we really realized that we had to look at things in a much more different way. And so that led to this whole journey over the last several months to create a unified data and CVML platform, which now at the heart of it has 5 foundational pillars. The biggest pillar, of course, and there are several pillars, but one of the crucial pillars is the data foundation, which in addition to AWS now has a large Databricks presence. We are building applications, which are already there, but taking it to the next level of maturity, which help us with our entire image data curation. And it's a pretty crucial ecosystem because that's the heart of how the model utilize all of these images. The ML systems, in addition to Qflow, have been expanded to have an on-prem presence, and we'll talk a little bit about it more in slides later, but also utilizing the best of new things that are coming out from our partner, that is Databricks. In today's demo, you will walk through, you will see how we've run a distributed machine learning pipeline on the Databricks ecosystem with some of the very recently released features. And lastly, I think as a conscious choice, I think integrations for doing things was an important architectural and guiding principle we've used in the journey where we are. We could have built an entire image curation system, entire labeling platform all by ourselves. But this world is changing so rapidly in that area that for us it made sense to actually integrate with the best and world-class vendors that we have today. We use Labelbox as our labeling platform, and we've even expanded to use their data curation capabilities. We also have integrations with weight and biases and other model diagnostic tools. A few we couldn't mention because contractually, but there are actually a few more tools in the equation and vendor integrations that we've not shown on the slide, but they are there. And all of this built on top of a hybrid infrastructure, both cloud and on-prem, with the best practices in DevOps, DataOps, and MLOps, because that's really key for us to scale. Moving on to the next slide. So let's talk about the data foundation. And this is where Databricks is actually a central part of our data foundation. I am not able to look at it, but OK, I'll try my best because of this thing. The foundation on Databricks provides our program teams. So we are platform teams, and our end users are program teams. That's what we call them. It provides these program teams, as Fahad said, very savvy engineering teams, cutting edge engineers working on robotic systems and computer vision. They want control. They want speed. They want flexibility of their systems. And so using Databricks with its independent tenants of Databricks workspaces for each, we were really able to achieve this. We as a platform team actually manage the life cycle of all the entities that are involved here. And these entities include images, annotations, model evaluations, etc. We manage them through platform APIs. And then the data related to these are exposed to the team through a set of Delta tables on the Databricks interface. The idea of letting governance, because people who are closest to the program are the ones most knowing what the data rules should be. And so the governance of this is enabled through a shared single Unity catalog at the whole BRT organization level. These workspaces, again, in the spirit of abstracting complexity, the ability to manage, we have infra as code that takes care of creating any necessary AWS and Databricks resources, service configuration changes, and continuous configurations that are needed as we integrate with different vendors and build new workflows. And last but not the least, our program teams definitely, absolutely needed the ability to spin up compute clusters for their needs as they need. They do all kinds of experimentation, exploring, and so they needed the ability to not depend on someone centrally to give them compute. Databricks has definitely helped us significantly in this regard, and we use these capabilities to enable the teams. So an important part of it was oversight, because one of the big things is, yes, you've enabled everyone, everyone's creating clusters, so you need to keep an oversight of costs and tracking dashboards. So we built a lot of cost tracking and other metrics dashboards to make sure we have a good idea of how the infrastructure is being used. All right, moving on. Fahad, you want to walk us through a high-level description?
So I think one of the things we wanted to do is we wanted to talk in terms of a use case that we actually have and take you through this journey as we worked on it with multiple different partners, including Databricks. So at a high level, it used to take us weeks to train machine learning models. Our North Star goal was to actually make it happen within hours. So that's what you see over here. develop and train a perception-based model within hours. And how would we measure the success by is, can we do this again and again? Can we make this repeatable? Can we make this continuous? So that's our North Star, where we can release new models within hours rather than weeks. Yeah.
So before I actually dive into the details of the machine learning model, we have to save the best for the last. So I'll go through the phases of the CVML cycle. And there are really three primary phases. Not surprisingly, of course, ingestion and data processing is the heart of any system. So that's obviously the phase one. The next phase in CVML, in computer vision systems, is a lot around data curation and labeling. And last but not the least is model training and evaluation. So let's look at the data ingestion process. Overly simplified diagram here, just really for the purpose of context setting. So all it's doing, it's showing is that we have data that we collect from machines. And primarily this data is machine logs and images. Again, a very simplified view. There's a lot of details about kind of logs, but very, again, simplistic view for the sake of the presentation. That is taken and uploaded into the cloud and then made available in Databricks for all kinds of purposes: experimentation, exploration, labeling operations, and model development. So with the context set, I think this is probably where there's a little bit more interesting work that we have done. As in the beginning, all of our program teams in several different programs, they were all each having their own version of a data ingestion pipeline. And what we realized was very soon was the processing need was pretty much same. They all had data in robotic data formats that needed to be converted over. In some cases, it was actually the exact same data set. It was just powering a different use case for a different program. So as we looked at it, the obvious and the most basic question was, is there a way to do this a little bit differently, a little bit more efficiently? And so that led to the creation of this common data ingestion pipeline, where you see the data, the robotic and edge system data, it makes its way into the cloud. And here, we convert it into these are mostly because they're robotic data logs. Some of them are standard ROS data formats. Some of them may be proprietary data formats that we built within BRT. These are then converted into an MCAP format, which is a new generation, next generation file format that has come from ROS2. This has enabled us to now, this transformation into MCAP has enabled us now to natively use this data into our Foxglove robotic data and interaction and visualization platform, which is really powerful, because a big part of our learning is understanding the machinery that we have built. Where is it running into issues? And spending a lot of time gets spent in machine diagnostic. And this integration pipeline to a robotic visualization system was a really crucial aspect of adding efficiency. What other things there? I think that's it probably. OK, last point around Databricks. So this data that we have, this MCAP data, is also, we have brought in, and it sits in the Databricks in a Delta table, which then actually opens up a whole set of CVML post-processing that you will see in the subsequent slides. All right? Next cycle. The next cycle in the CVML, as we flashed earlier, was the data curation and labeling process. As I explained earlier, we actually rely on external vendor integrations in this area of labeling and curation. And as a conscious choice, where we see literally even the LLMs coming in disrupting the whole labeling space. So for us, for the agility that we needed, it made a lot of sense for us. And we work with a vendor called Labelbox. It's kind of leader in its labeling space. And these integrations that we have built with this labeling vendor, we've embedded these integrations in our life cycle. It helps the team. So end result of this integration is it helps us find that needle in the haystack, that really relevant subset of images that we really need to be able to sample and send for further processing. And before this process would take it was a very painful process. So to explain and highlight what the pains in a vision system are, this next slide should help us a lot in understanding that. Usually the process of data curation in a vision system starts with some basic metadata enrichment. These could be custom feature extractors that our engineers make by themselves, Or these can be actually out-of-the-box things, like object detection from services like AWS recognition. These are then, in our system, we've actually created integration notebooks on Databricks that bring the capabilities of having an image catalog to life. Once the capabilities of image cataloging are available, our data scientists and machine learning engineers can now start to do really advanced image data curation by using similarity searches, natural language processing searches, other metadata augmentation. The end result of this is that you now get a really refined and fine-tuned data set that we have also automated such that this refined conditions defined are applied to every incoming image. And that is a huge processing gain. That is a huge efficiency for people who spend hours just trying in a billion of image, trying to find out which images should I really use for this model training. Huge, huge efficiency gain. So now that you have a curated data set, it's actually the next step is actually sending it for labeling, because now you have a curated data set. We sample it, and we use a model-assisted pre-labeling process using data from a production pipeline, actual production models. This is then sent where there's a human labeler who then labels and sends the data back. And when it comes back, we actually have, in the past, we didn't have that. This was effort of some of my team members who are present here, who actually built a model-assisted quality pipeline, which what it does is it's essentially a pipeline that runs on Databricks, and it helps create an ability to create a smart audit kind of dashboard that finds out whether there's discrepancy in the human label process from what the model actually thinks it should be. And then finally, with the output finally ready, as you can see, it's a pretty involved process. This is why these systems are hard and difficult to build. And the end output is, at the end, OK, finally, the program team data scientist says, are you done? Do I have my data set that is ready for training? And we say, yes, here you go. It's available for you, available in a Databricks environment, in a Delta table for you to use, or in S3. It's a combination system that we have today. Moving on, model training and evaluation. And not surprisingly, this is actually one of the most important and most crucial phase, or the area of focus in our organization, and rightfully so, because machine learning training of these deep learning models is extremely computationally intensive. And so for us, it is imperative that we keep an eye on this area, both from a cycle time perspective and from a cost perspective. So it has a direct return on return of investment and developer and operational efficiency. Today, like I described before, a lot of our production pipelines, they have been running on Kubeflow, and they've also been running on on-prem. However, we've been facing challenges with our Kubeflow world. Not that Kubeflow itself is bad or something. Some of it were design decisions that were made early on the last 2-3 years as we've built those pipelines. But some of it is also beyond outside of just what design we put up. It has to do with the complexity of managing such an infrastructure for machine learning in this open source environment. And it has to do with being able to provide the right level of isolation for our program teams in a shared workspace, because everyone's fighting and wanting for the same compute resources. They're fighting for the same compute resources. Everyone needs those GPUs in a given point of cycle in a season. So as we looked at this, there was also another third important angle, as Fahad's already alluded to. Some of these models, the perception-based models, especially the self-driving ones, they were taking days, maybe even weeks. And so the idea of having a solution that saved us, or creating a layer, hiding the complexity of this infrastructure, and being able to do some of this processing in a distributed kind of way, with maybe multi-node distributed ML training, is actually a very appealing possibility to us. And by chance, we happen to engage with Databricks on a professional services engagement, I think, that has helped us leap a lot faster in the last quarter in this regard. So let's understand and talk. But before I do that, this is our Oh, I do have to click it fast. Why is the tractor not moving? Oh, it's moving. Okay, and it's stopping. Okay, all right. So this is a real world. This is our real tractor. It's actually in the field. This is not some made-up images. This is actually happening in a Gilroy field, if you're interested. That's a very nice place from BlueRiver to visit. So what is the job? What is this self-driving use case model actually trying to do? It's actually three things. Its focus, it has to sense. It has to sense what the real-world objects are in the environment it is operating. It has to think that it is to classify what this object is and whether it cares about this object in a meaningful way. And the objects that we care about really right now are humans, of course, because it's all about safety. The tractor has to stop. It's an autonomous tractor, but it needs to stop if there are humans to slow down. Or it can be many different objects. It could be trees, it could be vehicles, farm equipment, utility poles. Our teams are even gone so advanced that it's flying debris. It's even arcane, obscure conditions that you might think, oh, why would anybody be looking for that? But we do. And I think there's an additional level of complexity because you do this in conditions which are low light conditions, dust, because it's a field. Fields have a lot of dust, and rain or cloud, storm or snow, all kinds of conditions. So doing this in a very meaningful way in these kind of ecosystem is a pretty challenging ask. So one more thing that the model has to do is actually it needs to understand how far it is from the object that is considered as an obstacle. So it's essential to create a depth map and know, oh, I'm 50 feet away, whatever the configuration might be, I have to stop when the obstacle is that far away from me. So even, and I'll talk a little bit more about the details. But essentially, as you can see, there'll be some significant compute needs to develop this kind of model. Going into a little bit more detail, an actual image from an actual field of ours, taken from our web app. So here's a system. You see the way the images are captured, they are from a stereo image pairs, these images. They are obtained, and then they're fed to our computer vision neural network model. This model performs a semantic segmentation. For people who may not be familiar, semantic segmentation is basically taking every pixel in the frame, and it is determining which type of object it belongs to. As I already explained, the objects our model is interested in. In addition, I explained that we had to have a depth map. This depth map actually is produced by another machine learning model that we have from the Sage image pairs. But we have to take this data from this depth model and this semantic image classification, combine them together. That creates the complete entire training job. So as we said, compute-intensive pre-processing step on the depth map, and the compute-intensive training pipeline with semantic segmentation. Parallelizing these workloads, as you can see, is a real necessity, right? That really needed by our program teams. Our biggest challenge is, so we do use GPUs, but the biggest challenge in achieving the efficiency use of the GPUs for this training was making sure or ensuring that this I/O layer that we have has enough sufficient throughput so that it can saturate the GPU, or you have an underutilized GPU. And the way we have built the architecture here, by creating a delta life, I wish there's a way I could pinpoint that, I'm not sure. But it's the delta table in the center, which is the pre-processed image and metadata set. It combines the image data and the descriptive metadata into that common delta table that you see in the center, and almost a materialized view, such that now we no longer need to read small files directly from the file storage system. This is where a lot of efficiency has been obtained. This way, by not reading small files from the storage, we've actually increased the I/O throughput and created the necessary saturation conditions at the GPU layer. The data from that delta table is actually read through the Delta Torch recently released, Databricks recently released Delta Torch library that we are using in conjunction with another interface, which is the distributed Torch distributor. People may have been using in the past things like Horoward for achieving a data parallel processing in machine learning training steps. With this new advancement that came from Databricks, we felt that it was at least worthwhile trying this. There is a model that we have that does use Petastorm and Horowat, another different model in another program. But for this autonomous tractor model, we did decide to experiment and use both the new capabilities, the delta chart capability and the torch distributor capability. What we found is, as compared to Horowat, there was a little less low-level API programming interface that we could deal with. That was a benefit for us, and a slightly bit cleaner interface. Of course, this is a bit early on, so we are still continuing to try and test this pipeline. So coming to an end, I've been speaking for quite a while, but I will hand over to Fahad quickly. Where are we with things? We've seen, as he said, very promising result. But we have to test a lot and see how this really performs. Our world of ecosystem, to be quite honestly, is going to be a hybrid world because machine learning is the bread and butter of our company. So running everything on cloud isn't a proposition that we think we can totally embark on fully. We're continuing to have a fine balance and a good line between an on-prem and a cloud training is the key what we're looking. What is really promising to us, what gives us hope is the way how quickly a lot of these cloud platforms are coming together to blur things. Even with the announcement of Mosaic, one of the main reasons our teams actually went to on-prem is not that they wanted to sit and manage on-prem. Nobody wants to do that these days. But it was the guarantee of actually available GPUs. They knew they were set. But it is not an easy thing because there's another complete different trade-off to that world. So with the advancements that are happening with companies like Databricks doing things with Mosaic and other capabilities, we think that the world is coming together. So we definitely wanted to experiment. We have a world set and going with our Kubeflow. We continue to invest and improve things. But we definitely do not want to stop there. We as a company are all about cutting edge innovation and trying what the best of industry has to offer with the partnership. To us, it made a lot of sense to try Databricks because Databricks is a foundational data lake house, and doing it a little bit more natively and seamlessly, trying and experimenting with us absolutely made the most complete sense. So with that, I think we would love to hear ideas and thoughts on people who have done very creative things, so do reach out to us. With that, we have Job. Oh, no, Fahad, actually, that's later. I will hand it over to you.
No worries. So yeah, just to finish it off, as you can see, it's quite a complex ecosystem with quite a few things going on. And at a high level, we just want to be cost efficient. That's one of our driving principles at both Deere and BlueRiver. So, three driving principles: continue to innovate faster, continue to scale, but continue to be cost efficient. And that's about it. The last thing we have here is a barcode. If you think this is exciting stuff and you want to join us at BlueRiver, you can scan this, check out our job listings. Would love to have you in being part of revolutionizing agriculture at BlueRiver. That's about it.
Thank you.